All right, so for the last couple of sections, we'll wrap these notes up. All right, so the first one, we talked about this a little bit before, but the two main motions that the Earth goes through, the first one being rotation. So the Earth rotates on its axis. That takes a little over 24 hours, 24 hours and some change. That's why you have to have leap years every 4 years just to make up that extra little bit. The Earth's rotation is also why sun rises in the east, sets in the west, all that. All right, second main type of motion is revolution. So the Earth revolves around the sun, and that takes 365 days and some change to get around the sun. Again, that extra little bit, that's why we have a leap year every 4 years, and we have February 29th every 4 years. So, so rotation and revolution are the, by far the two main motions that the Earth goes through that impacts our daily lives. No problem. Couple of terms, the perihelion and the aphelion. I'm not going to focus on these a ton, but perihelion is when the Earth is closest to the sun, and the aphelion is when it's furthest from the sun. Also a good reminder that the seasons are caused by the Earth's tilt on its axis. It has nothing to do with the distance from the sun. Because, here we have the perihelion when the Earth is closest to the sun, and that's January 3rd, which here in the Northern Hemisphere is in the winter. So that completely contradicts the whole idea of, well, the seasons are caused because we're closer or further away. So yeah, remember, seasons are caused by the tilt of the Earth. Right, precession is the kind of the third type, or the third movement that the Earth goes through. The example of the spinning top, as the Earth rotates on its axis, it doesn't just rotate perfectly. It has kind of a wobble to it, kind of like if you spin a top. And it spins real well at first, but then as it slows down, it starts to wobble. The Earth kind of does that as well. But it's a really long cycle. It says, about 26,000 years for it to go all the way around that, that wobble. So it's a long cycle. There's some scientists that believe that this is the reason we have ice ages periodically, is because of that wobble, puts the Earth, in more of a tilt. And so it leads to kind of more extreme weather and climate change. Then on to the moon a little bit. So the same prefixes, the perigee and apogee. Instead of helion, you have G. So when the moon is closest to the Earth and when the moon is furthest from the Earth. They're both thinking, pretty good distance, but the moon is the closest object to the Earth. The sun is the closest star to the Earth. But because the moon is so close, that distance, that change in distance, does make a difference in how the moon looks. So, if you've ever noticed, you look up at the night sky and the moon just looks big, it could very well be taking up more space in the night sky because it's closer. It's a distinct possibility. Phases of the moon. So the way the moon looks, I guess would be one way to say it, that changes during the month, during the lunar cycle. All it is just different amounts of the lunar surface are illuminated by the sun. Also, the moon does not produce light; it just reflects sunlight. So the moonlight that you see, it's just reflected sunlight. It doesn't come from the moon. The moon doesn't produce it. Right. This shows us the different phases of the moon. So we have the sun over here on the right. When the moon is between the Earth and the sun, that's what we call a new moon. So we don't see any of the surface of the moon illuminated. And then as the moon is revolving around the Earth, we start to see more of the surface illuminated, up until the point where we see all of the surface illuminated, so as a full moon, and then it starts to get smaller and smaller. Excuse me. So this little animation shows something that's kind of cool, because we only see one side of the moon. The way that happens is the amount of time that it takes for the moon to rotate once on its axis is the same amount of time that it takes to revolve around the Earth. So as a result, we only see one half of the moon. So the term like dark side of the moon, there is no dark side of the moon. It's just like saying the dark side of the Earth. At any given time, half of the Earth is light and half of it's dark. Just like any given time, half the moon is light, half the moon is dark. There is a backside of the moon that we don't see, but we only see one half of the moon. So there's no dark side of the moon, but there's a backside to it. Excuse me. The moon plays into the tides. So the gravitational pull of the moon affects the ocean levels. Also, whenever you have the moon and the Earth and the sun all in the same, line, that can affect the tides more severely and can give rise to higher tides and bigger changes that way. And then anytime the moon is 90 degrees to kind of the line that the Earth and the sun, on either side, but it's 90 degrees. That's called a neap tide. Whereas the other is a spring tide. All right, on to eclipses. Eclipses are named for whatever is being blocked out. So if it's a solar eclipse, the sun is being blocked. And that happens when the moon passes in between the sun and the Earth, and it blocks out the sun. What kind of causes that is basically just the moon's shadow. It's coming between a certain vantage point on the Earth and the sun, and it'll block it out. If it's the total eclipse, then you'll see something that looks kind of like this. You'll just see the outer, what's called the corona of the sun. But if you're outside of that, very small area that sees this, then you see a partial or maybe no eclipse at all. This is a picture from the International Space Station of the solar eclipse. So this is just a picture of the moon's shadow moving across the surface of the Earth. Which you don't really think of planets or moons exactly casting shadows, but they do. Then lunar eclipses. So this is when the moon is being blocked out, and it's being blocked by the Earth's shadow. So whenever the moon passes through the Earth's shadow, then that's a lunar eclipse. Lunar eclipses are more common than solar eclipses. You may be thinking that, you know, if you have the Earth and the moon is orbiting the Earth, then why don't we have more eclipses? And we would if, you know, if this is the plane that the sun and the Earth are in orbit-wise, if the moon orbited in that same plane, we would have more eclipses. We'd have one, you know, we'd have multiple every month. That's not the case. It's the moon's orbit is not in the same plane as the same plane that the Earth and the sun are in. So that's why we don't have eclipses every month. All right, and the last little section of the moon, kind of buzz through this one. Craters. So it's any sort of you know, indentation, depression that's caused by some sort of an impact you know, on a planet or a moon. The craters are especially on the moon, because there is no atmosphere, because there's no air, there's nothing to slow anything down. So things moving in space move very, very fast. I mean, right now the Earth is rotating at about 1,000 miles per hour, and we're moving through space at about 17,000 miles per hour. You know, so it's very common for things to move at very, very high rates of speed because there's nothing to slow it down. There's no air to slow it down. That's why most meteors explode in the atmosphere or burn up in the atmosphere. And then they, you know, could potentially impact Earth because they're moving so fast that once they enter the atmosphere, the friction and the resistance from the air itself heat them up to the point where they, you know, burn up or explode or something like that. And then the rays, these are just formations created from impacts. So here we have a picture of the moon. See some craters, some big ones like Kepler crater, Copernicus crater. You can see these rays like radiating out from that crater, those lines that are radiating outwards. Those are rays. And there's just a diagram showing formation of a crater. Not too exciting there. On the moon, there are the highlands, which is kind of a lighter colored area. And then there are the Maria, which are the darker areas. Those darker areas are made out of cooled basaltic lava. Moon rocks are just like Earth rocks. They're igneous rocks. They're rocks with basaltic composition, granitic composition, just like there are here. It's just that they're on the moon. The lighter colored parts of the moon are covered with lunar regolith. It's, you know, light gray, very fine, almost like a powder. If you've seen pictures of the footprints on the surface of the moon, that's what the footprint is in this lunar regolith. Because there's no atmosphere, there's no air, there's no wind, so there's nothing to blow it away. Whereas here, I mean, it's such a fine material that it would blow away pretty much instantaneously. But up there with no atmosphere and no wind, it just stays there. And this is just kind of a little depiction of kind of the most widely accepted idea of how the moon was formed. Was that while the Earth was still molten, it was struck by a planet-sized object, and that ejected a lot of material out into space. That material then started to orbit the Earth and came together over time to form the moon. which would explain why moon rocks are the same as Earth rocks, because it was part of the Earth at one time. So, that's kind of the most widely accepted thought on how the moon formed. And since it is May the 4th, may the 4th be with you.